So we just thought we'd do a bit of a group discussion about how to engineer super homes and
build them.
and build them and design them.
Yes.
And yeah, so my ears are still ringing and my head's still spinning from the Cult concert last night. So I thought I'd better get some help with this webinar. Um, so yeah, so we'll just crack into it. And if you have any questions, pop them in the chat and we'll get to those. But I thought, maybe you guys, I might just ask you guys questions.
Yeah, go for it. Sounds good. Fine.
Yeah. So there's our top 10 things. It's not exhaustive, and there's crossovers but yeah. Superstructure. So we're talking about floors, walls, roofs, windows. It's all part of the structure, part of the building envelope, but with more of a structural focus today than a thermal focus. But I think a big part of it is actually how everything is coordinated and interrelated. So what we have found is that just teamwork makes the dream work. So just getting everybody together at a very early stage, conceptual stage, and working out how's the structure going to fit in the building and how are the services going to fit without colliding with the structure. And that's really, really valuable. And yeah, bringing in the ventilation people into those early meetings as well. And yeah, just working out how the designers' crazy ideas are actually going to stand up.
We need to steel in there. We love steel. Engineers love steel. Superhomes don't.
Yeah. So good point. So thermal bridging,
yes,
or cold bridging, whatever you want to call it.
Yeah.
Thermal bridge-free construction is what we're aiming for.
And then I guess just leading off from exactly what you said, I couldn't agree more that early consultant and contractor involvement is absolutely key, particularly to engineer a lot of the steel out. It obviously has its place. Sometimes you need portal frames or a beam, but keeping it within the thermal envelope to reduce cold bridging as much as possible, and that's where those early meetings really, really help. And just designing with as much timber as possible to obviously reduce that thermal bridging down as well. Because as a lot of engineers would know now, and even architects, there's the ProLam portal frames are really, really good. Your typical living, dining, lounge area, we've got the big sort of wings, and at the end you typically have glass there with no wing walls for bracing. So that's always where you want to, 9 times out of 10, you see structural steel portal frames there, but you can do that with timber now. Really good to work with those guys too, as we've done on a couple of projects.
Yeah.
So.
I think too as well for this early engagement is we've been utilising it a little bit lately on the more technical jobs where we're using BIM modelling. So we can basically build it in virtually before we build it in reality, which we've used offsite design for that. So that helps out, and it can iron out a lot of issues at the front end, which means you don't waste time on site, and you fix up of all the things that are not.
So almost like doing shop drawings, I guess.
Pretty much, yeah. And likewise, we're doing 3D modelling and sharing our IFC files with the architect yourselves at that QS stage as well. Irons a lot of that out.
Yeah. So these are our partners on the screen at the moment in the Superhome movement, and there's I think there's 3 engineers, structural engineers that are Superhome, 3 or 4 who are Superhome participants. There's probably about 20 or so builders, and probably about the same number of designers. But I think it's a really good start to kind of engage with one of the participants in the Superhome movement, because they're the people that get it, and they're the people that have been thinking about this and kind of understand the why and the values shared, sort of like-minded people that excuse me, share the same sort of values around when it comes to sustainability and climate change. And it's really something that I think is really important. I think it's almost like you need to internalize that to actually get it and to actually have that the detail come through in the design and in the work. So that's something to think about. And I love the fact that we've got the best builders, best engineers, and it's just been really great to connect with those people who are on the same journey. And so that's been important. So we'll just keep moving through these slides. So I was just going to mention just quickly, Quakestart, it's probably something that a lot of people don't know about. Yeah, you have that. So this is an idea that I had after the Canterbury earthquakes, and it came about from just, we couldn't get insurance, and we were thinking, well, okay, if we can prove that buildings are going to be a better bet for insurance companies when they're going to be more resilient, both more resilient in earthquakes and also the other extreme weather events, then that's going to be a surer bet for insurance. So I just had the idea, and then a guy by the name of Dr. David Hopkins, who's an earthquake engineering guru, created Quakestart initially for commercial buildings and then later for residential homes. So there is a app, there is a web app. So if you go to quakestart.org.nz and it's called House Check. So you can just click on that and answer questions about a home, and it gives you a rating out of 5. So there's 5 stars, 5's the best. So some of the homes we've done 5 stars, or probably most of them actually. And a lot of people aren't thinking about this, but I think some people are, and it probably comes down to people's experience through the earthquakes. And if people have been tipped out of their house, then their perception of building better than building code is probably more heightened. But I guess it's a little bit like the the energy efficiency part of the building code. The structural standards is really and Steve will be able to talk in more detail about this, but it's really about protecting from death and injury. It's not protecting your building. So with Quakestart, there's the 3 Ds: death, dollars, and downtime. So you're going to not die, which is a good thing, but you're also going to know if it's a high-rated building, it's going to cost less to repair it, and there'll be less time out of your building, and you'll be able to, a 5-star building, you'll probably be able to, there'll just be minor repairs, and you might not even have to move out. So I think that's a worthwhile thing to think about when thinking about a super home. And also a lot of the time doing better than code, say, 150, 200% even of NBS, new building standard, it's not expensive. It's just a matter of getting the proportions right and the openings in the right places and stuff like that. And these days having rigid air barriers on the outside, it's not expensive and not difficult to achieve these sort of standards of structural resilience. And Steve, I'm just thinking, there is these different levels in terms of, 1 in 500 year event, 1 in 1,000 year event. Do you want to just elaborate on that a little bit?
Yeah, so they relate to the importance level of the building. Most residential homes in New Zealand will be importance level 1, importance level 2. And that relates to the 1 in 500 year event for an earthquake, for example. So most houses we design to those. But on that note, when we do bracings for any sort of super homes, high performance homes, we target 150% for bracing. Code minimums obviously 100%. So going that extra is actually not much more. Maybe just massaging a few walls, and that's just kind of collaborating with yourselves and say, hey, look, can we have 100 more mils here or 200 there, or if we move this, we can do that. You get around using a portal frame. So it's no additional cost during the project to be getting 150%. And it also, we sometimes even go, there's a new National Seismic Register that's come out that some areas are going forward, going to have a higher seismic region, which is actually going to bump that up even further. And then you just have a bit of resiliency up your sleeve there as well. And you'll know, Dan, when you're at site, and sometimes you have the frame, you come to site and you see like 2 or 3 studs there, and you might be 50 or 100 mil short for a bracing element. So by going higher than 150%, that doesn't matter.
Yeah.
Well, the council gets picky, but that's another story.
Yeah. So I guess, as usual, the moral of the story is the building code describes the worst possible building that you're legally allowed to build. And I mean,
yeah, exactly.
The standard in terms of healthy, having a healthy home and having an energy efficient home is just woefully inadequate. And similarly, I think the 100% of code is going to be safe and protect you. Well, your building might not be safe, but you might not lose your life. But the fact that can be relied on is probably a bit of a fallacy, a bit like the other sections of the building code. So I would suggest that we need to do much better. And
everything we do, we're always at a minimum 150, even if it's not a high performance home, we still try and target 150 as much as possible. And I mean, everyone I'm sure who has seen, I probably shouldn't say names, but the likes of, say, Wolfbrook, your Brooksfield, your Williams Corporation homes around the place that will see quadruple 5, 6, 7 studs with knobs everywhere is just horrendous. You need to walk around the streets to see that. But from a structural perspective, you don't even need any of those knobs. You only need, 1 stud at regular centres. You don't need the groups. And that's where you get into the issues with bracing elements, because you've got the handy bracket here, and then you might have 5 studs. So you're not going to get that overall length you need, but again, you don't even need all of those multiples of studs that you see everywhere. So
I think probably coming from the earthquakes too, a lot of the time engineers were playing it over the top safe, weren't they? Just it's a butt covering exercise. So I think that's where it stems from a lot of the time as well.
Yeah, absolutely. And I've seen lots of other engineering designs where you can tell that they've just haven't actually taken the extra bit more thought and time to design it appropriately. And for example, you don't always just have to use a steel PFC. You can, tweak things a bit and get timber to work. There's SG8, there's LVL, there's Blue Lamb. There's so many other options from Nelson Pine and Lumberworks.
Yeah. So, I mean, we want to move on to looking at some details and some practical, easily implementable ideas next. But just before we get to that, I think just in terms of sustainable structural design and just thinking about, sustainability, I think reportedly 90% of the CBD needed to be demolished and rebuilt after the earthquake. Well, that's incredibly resource intensive, carbon intensive, and everything else intensive. And that's about as unsustainable as it gets. So if we can design buildings that are going to have more longevity as well, more durability, and also, so that's, I'll just keep moving on. It's almost like that little ripple was an earthquake there, wasn't it? Yeah. So we've already talked about this, the teamwork approach and early engagement, and just getting everybody together to look at a very early concept. So some of the products and systems that we're using in the designs, Dan, do you want to talk about this one?
Yes. So that was a project we did over in Cashmere Estate. So as you can see on the left-hand side there's a CLT mid-floor. The reason why that was utilised was because there was a recession plane and we were only 20 mils below that. So if we built up the mid-floor in a conventional way with joists and such things,
I think the height limit, we were 20 mils from the height limit.
So obviously that helped to keep us within that recession plane. So also gave us a good amount of bracing in the diaphragm as well, and acoustics. So multi-prong approach.
So it's really easy to design with. So we were the engineers on there too. It was really easy to design with, and then you had a clean services run beneath it.
Okay. So basically you can get away with a floor that's 160 instead of 300.
Mm.
You get that extra height.
And we had that, the good thing about that too is that the speed of it going down. So we weren't cutting every joist and laying them down. Of course, you can utilise that with a conventional joist system and make cassettes and lift them in. But for this case, for that recession plane, we got that mid-floor down in about 3 hours. So
and then you didn't have to worry about coming back in and having like services penetrations through joists and the like as well. So
so that was already done. So we had a service cavity underneath to allow for the ventilation. So in the ceiling space.
So this project here is a really good example of extensive use of or minimal steel. I think there's only one piece of steel in here. If you can see my mouse, I'm not sure, but it's just this window. And all of these large overhang roofs, and there's a cantilever at the other end of this building. It's all done with timber and sort of box beams with plywood, two sides. There's the entrance there. So the top floor cantilevers the bottom floor and creates a bit of a sort of sheltered entranceway. So Dan made the Ecopanels for this and installed them, and there was a different builder that did the rest of the job. But we'll talk about Ecopanels in a minute. But this drawing here just shows how we incorporated the steel so that it's within the thermal envelope, within the airtight thermal envelope. So if you do need steel, it's pretty much essential to not put it in the structural part of the wall that we want to be airtight and insulated. So what would normally be the services cavity and a 50mm cavity, I think we just thicken that up to 90mm on this one wall. And then that's where the structural steel was in that wall. Oh yeah, that other box there is really just the shutters that create the shading. So but yeah, there's always a way to eliminate the thermal bridging, and it just takes thought.
And the desire to do better.
Yeah, and like what we were talking about before, just sort of, understanding why we need to do this.
And good collaboration and teamwork between all parties as well.
So base, better, best. So, maybe we need a base, better, best for structural, a superstructure. Do you want to have a think about that for us, Steve?
So you start with steel and work your way up
or maybe it relates to what we were talking about before.
Or 100% there, and then working your way up.
Yeah.
And how you can achieve that.
I mean, I've worked with a lot of different engineers, and some engineers prefer steel, some prefer timber, some prefer concrete. We're definitely obviously, as we've talked about, we're trying to reduce the steel both from the thermal bridging point of view, but also as the embodied carbon point of view as well. And then concrete, I mean, you can do an insulated concrete home, and normally we'd be trying to insulate on the outside, either some sort of sandwich panel with thermomass panel, or having evened out insulate out. So have that insulation, outsulation.
So we're doing a project up in Kitchener's Knoll, which is in Redmond Spur, which is exactly that. It's a client system. So they've come up with a system where it's got a plywood shuttering on the inside, concrete, and then EPS on the outside, which all ties in together. And we've poured these in situ, and so it's just got about 150 mils of insulation on the outside, which then incorporates battens within the system to be able to hold the form in place while it's being poured, but then attach the cladding to. So
that sounds pretty interesting, eh? But the other thing is if you're doing, like, we've done a handful of insulated concrete panel houses, and we've detailed them so that the insulation is continuous at junctions and around corners and things. So you just I mean, it's just a matter of just thinking about it and detailing it that way. But do you want to talk about the timber walls?
So this is how we do all of it. It's on here. So the jib fix framing system, or it's been around for a wee while, but also in America it's called the California Corner. So just basically eliminating that the triple stud corners on the external corners as well as where internal walls meet the external. So regardless of whether you're what type of building you're doing, I think this should be the way it should be done, because it eliminates unnecessary timber and obviously allows for extra insulation, which is always cheaper than timber. Then it obviously minimises that thermal bridging, as you can see there.
I thought this would just become the new normal. You know, we did this. I think we were the first house in Christchurch that entered our home in
2015. Yeah.
Yeah, and I thought, well, if there's less timber and more insulation, the insulation's cheaper than timber, then why aren't all houses built this way? And it's just we've just carried on doing it the old way.
I guess that's one of the most used sayings around is it's how we've always done it, so therefore it should be right, which is not the case. You know, you should be able to adapt and move and just do things better each time. Every house you build, or every house that we build, we're always trying to find a little bit extra where we can do things better, which makes it more efficient to build, makes it less costly for the client, as well as just more efficient thermally. So
yeah. So the other thing is just leaving the dwangs out and or nogs, and then or if you do need dwangs, put them on the edge so the insulation can be continuous past them. But then Ecopanel, Dan, we have another layer of insulation anyway with this.
Yeah, well, also on that jib, that previous slide with the jib fixed system, it wasn't showing the service cavity, which you can see in that center photo there. So basically, the panels come to site fully from external cavity bed into internal service cavity. So that includes the RAB, airtight layers, insulation, all in one piece. So the panels can be, the largest panel we've done, I think, is about 12 meters long by 2.7 stud. So depending on site access and clients' budgets to how big the panels can be with freight, it's pretty easy to do. So and the good thing about that is that the speed at which they can go up, which eliminates can reduce your overheads with P&Gs and labour on site. So it's all done in a factory. And if you're thinking about building it on site, like on a 2-storied house on a hill, then you're taking one piece of ply up, nailing it on, cutting it, and doing it like that. It's really repetitive. It takes quite a long time. So we've had jobs that we've got weather tight on a hill in 5 days using panelisation. So
yeah. I mean, you see framing sitting out in the rain for days or weeks, then just deteriorating. But it never gets wet because it's wrapped when it gets delivered. But even renovations, we're achieving this same sort of build up with a renovation that Dan and I are currently working on. We're putting ply. We've removed the existing linings, and put ply on the inside, and then putting an internal services cavity into an existing building. Do you want to talk about that?
Yeah. Well, so it was a 1950s house. So think of a red brick, Remu framing, diagonal dwangs or nogs to create the bracing. So basically, what we did is we stripped everything off the ceiling, basically back to Remu or back to the framing. Included removing all the dwangs that were in the exterior wall. So then what we did is we wrapped a weather tight layer around the studs and started instead of trying to Christmas wrap in between each pocket, we just ran a continuous layer
in and out of the studs.
In and out of the studs. So and then inserted the insulation and then put the plywood on top of that, which for 2 reasons. So we got our airtight layer, but also to give the house some structure as well, because obviously there was a time before bracing was a thing really.
So basically what's in tallow here in that
plywood
situation is plywood, and it's giving you the bracing as well
as the airtight layer. So.
And then you just tape the joins so that it's airtight as well.
So tape to the floor, tape to the Intello on the ceiling would run to the plywood, and then we'd tape to that. So
So I've actually seen some new houses being done recently where they've used plywood as the airtightness on the inside of the wall, which just puts your bracing on the inside. So this old chestnut, this old favourite, we're talking about the building envelope, so it's worth mentioning. We should stop putting our windows where the building code tells us, on the outside of the cladding. So we've been banging on about this for a while now, and just recently, even the good old aluminium companies have come out with
Some recessed
some
windows.
recessed window detail. Yeah, I mean, I guess the windows are still going to be probably not that airtight and not as good as, say, PVC or European style windows, but at least they're trying. At least they've brought out a detail. So it's good to see them at least, yeah, like you say, taking a step in the right direction. So we won't dwell on this because we've covered this several times in the past. Super versus stupid. So many things that we do that are stupid.
That's how we've always done it.
Yeah.
Foundations, Dan.
Yeah, so as you can see there, on the picture on the right-hand side was of a project we retrofitted insulation to the edge. So it had fully insulation underneath, but I took a photo with the thermal imaging camera, and you can see the yellow there. That house was just finished. No one was living in it yet, but you can still see the heat escaping. So that just goes to show the importance of insulating the edge of the foundation, not just the underneath. And anyone who tries to tell me otherwise, I'd sort of laugh it off really, because it just needs to be done. I think there's
always a few non-believers, naysayers.
Yeah. Actually, we did a couple of talks at some conferences. We had some bit of a heckler saying you don't need to do it, and it was like, well, there's the photo, there's the evidence why you do.
Yeah. Similarly, if you take a photo of a wall where you've got the extra services cavity, you'll see that that's eliminating the bridge where the studs are, because the only point where you've got a thermal bridge is where those two timbers cross, which is
yeah. If we go back to talking about walls, and if you were making a decision to say yes, I want a thicker wall, and you're debating whether you go a 140 stud, obviously with no dwellings if you can avoid it, we can avoid it, versus a 90 with the surface cavity. It's actually, you'll get better performance out of the 90 plus the surface cavity. You get the same insulation value, but because you're having only a 45 by 45 area where there is potential thermal bridging versus a stud going all the way up. So
yeah, and you're only talking about the external walls. So I think it adds surprisingly little extra cost just to put some horizontal battens and an extra layer on the external walls.
Well, I think there's a slide coming up of a project we're doing, and well, there you go, there it is there. I did when the people started talking about the rollback on H1 insulation levels and stuff, I sort of did some figures.
Minister Pink.
Yes, did some figures around.
Suggesting pink bat.
Did some figures around the cost benefits of doing, the extra layer of the insulation, which was only about $2,500 over this house. There's about 167 squares on the floor. Also with the walls, to add, by the time you take away credits for the triple studs, the extra row of dwangs, I think the uplift in cost to do the surface cavity plus the insulation on that house was, I think it was about $1,200. And if you were doing a surface cavity plus insulation with a 6x2 wall, the previous one was a 90 mil wall, but the 140 stud was only $550, because obviously you're still putting the surface cavity insulation in regardless, but the cost per linear meter obviously for the 6x2 framing is more than the 4x2, so hence why it's a lesser cost. So it's a no-brainer.
Yeah, so I mean, you'd save that in your power bill, wouldn't you?
Yeah.
On the first year, probably. So roofs, another silly thing in the building code, this idea of having 500 millimeters around the edge of the roof, where you can have the old standard, half the insulation, completely bonkers. I mean, the heat will go to the weakest link, and, the external perimeter wall there's probably likely going to be windows there too. That's where the most heat loss is going to be. And then you definitely don't want to reduce the insulation at that point in the roof. So there's ways around that. And yeah, maybe I've missed a slide. Oh, here we go. I'll just jump forward. So, I mean, you can increase the height of the truss heel. Commonly, we're adding an extra cavity, kind of like your wall services cavity, but on the ceiling. We're putting a 90 mil cavity In the ceiling, so basically, so our ventilation space, our ventilation ducts can go across the bottom of the bottom chord of the truss. So if it's required, you can fill that space with insulation as well.
Which is the same for if you do a skillion roof as well.
Yeah.
The good thing about lifting up the heel to make make that insulation layer continuous right to the outside plate is it'll give you a larger overhang as well, which will help with shading as well. So so it's a double benefit.
Yeah, which is a common it's a common problem with Kiwi homes. People don't think about overheating, and climate change. We're living in a warming climate. It's only going to get worse. So we've got to design for. I think when there was this sort of furore about winding back H1 changes, one of the comments was that the adding insulation was going to make houses too hot. The thing that makes houses too hot is faulty design. It's not more insulation. Actually, more insulation is going to make it cooler.
Well,
because insulation works both ways.
Well, I mean, if you think of it like a chili bin, it keeps whatever's in and whatever's out. So if the heat's in there, it's going to stop it from escaping because the insulation is doing what it's supposed to be doing. Now you've got to stop that heat from getting in there, which is, like you say, it comes down to design. So
yeah, it's just disappointing. Even people in positions of authority and people that should know better, should have people advising them about these things. They just don't know
what we're talking about.
And I think generally New Zealand building and the New Zealand public as well as the industry to a large degree, often people don't know what they don't know, and we think we know how to build, but it's a bit more complex than people really give it credit for. And so just getting the right people involved, trusting the experts is really important.
And it's okay to say you don't know. We don't claim to know everything about it all, so we're still learning every day. There's always something, better way of doing it. So, there's loads of people around to seek advice to get the experience that people have already been there and done it. Yeah,
and because I think that's the philosophy with the Superhome movement and the ethos. We're just sharing all our ideas because we're learning every day. So by the time we pass on the information, we're actually moved on from that and we're doing something new. Like our big thing that we're sort of up to our eyeballs in at the moment is embodied carbon and building New Zealand's first zero carbon superhome. So I'm a big fan of these warm roofs, Dan. We're doing a few of these.
Yeah. So that was from Kirkwood, the big cottage. So the structure in behind that you can sort of see in the top left-hand of the left-hand photo there is glulam. So similar in essence to CLT where it's mass timber, but it's running a different way. So those glulam panels are 600 wide. I think they were 900 wide.
PLT. Parallel laminated
yes.
instead of cross-laminated.
Yeah, so they were 900 wide by about, the longest one was about 12 meters. So they were all crane in position. Then on top of that, once the structure was fixed down to the engineer's specifications, we then laid 90 mils of PIR, as you can see there, on top, which created a warm roof. So we not only we have the R value on the timber, but also the.
So what does PIR stand for? Price is ridiculous.
Yes. yeah, it is.
Polyisocyanate, but yeah, it's a foam, basically plastic, extruded foam. It'd be really great if we had wood fibre in New Zealand where we could use a sustainable low carbon.
Well, funnily enough, we've got a project coming up where we're doing that. Another warm roof with wood fibre.
Yeah, so really common overseas. We're just starting to see it appear in New Zealand. But yeah, we're kind of at the bottom of the world. So some of the new.
So if we could stay on that one, the good thing about, and the same thing with the project up at Balmoral Lane is we're using a warm roof there. This one here had is it Gerard shingles on top?
Yep.
So we had the PIR, the weather-tight layer, which is Proclima Mento, and then our cavity batten and purlin. So we had a vented roof space. One up the hill is basically PIR as well as TPO on top. So a different, similar structure, but different roof coverings on that. So
yeah, so that was a flat panel roof, and then the falls were created by the insulation material, and it's quite a large house. So we ended up with quite thick insulation, and to save cost, we used a combination of EPS and PIR. So there's you can't adhere a membrane to EPS, so the top layer needed to be PIR, but the bulk of the insulation material, which was cut to create the falls, was the cheaper EPS, which is expanded polystyrene. Lots of acronyms.
And the good thing about the design of the one up in Balmoral Lane was the fact that the CLT could span both ways, but where we needed the windows hard up to the CLT, we had beams obviously across the top, so it's hidden within that warm roof, so then you get no thermal ridging as well. So it's a benefit.
Yeah. So the thing about these warm roofs is you just not creating a dew point within the structure, which is a big problem in terms of condensation and mold growth. So it's safe, and it's where the insulation should be. If in doubt, insulate out. So, yeah, that was your yeah. So this house here. Why did I include this? Oh yeah. So this was the one that we did a Quakestar house check, and this was 5 stars on that. But yeah, and the client was really interested in that, and they wanted, because they had to move out of their house, and they actually were moving back from Wellington, earthquake refugees. They left Christchurch and after the earthquakes and moved to Wellington, an even more earthquake prone place. And then they came back to Christchurch, and they wanted to have a house that was going to be their forever home, which is a common request from Superhome clients. They want this to, they quite sort of morbidly say they want to be carried out in a box, and this will be their last home. So they wanted it to be Quakestar, LifeMark, 10-star, passive house, all of those good things. And yeah, so and then this was a really good example of that, what we were talking about with that early engagement. So this the builder for this project actually built a model of the wall that went through the middle, and this if we go back to the plan, this wall through the middle housed a lot of the ductwork and the services. So that was very functional, not just sort of for the look.
It's an interesting thing about that wall is it looks like people would say that the stone's going right through, which is creating a thermal bridge, but obviously it's not. It just looks like it. So
yeah. Some people say, "Oh, is that a heat sink? Because that got like thermal mass?" And it probably not. Maybe a little bit, but not much, because it is just a timber frame wall with a thin veneer. And just incidentally, that veneer, that if I go back to that picture, or have a look at another picture. It's on the inside as well, just to create that illusion that it is a solid wall. But that veneer is so much more resilient in an earthquake. So what I noticed after the Canterbury earthquakes is a lot of the traditional schist, the 140 stone, was on the ground, and basically the only thing holding that together is gravity, whereas this is actually glued on. And the homes that use this veneer product were completely undamaged in the earthquakes. So it's just another good reason. Sounds like I'm a salesman for stone. Yeah. Anyway, so this is a house that incidentally is zero energy. So these solar panels produce more power than the house actually needs over the course of the year. And that includes running their electric vehicle. So free power for the house and free running of their car, which is pretty amazing. So how are we going for time? Oh yeah, so this was the picture that this is what I saw basically when I came out of my house day of the earthquake. Took 9 years to get the insurance paid, and then it took about 1.5 years to repair this house, which was sort of moderately munted. after the earthquakes. But we did a lot in terms of structural strengthening, and we made sure that we thought about this, where we're adding structure, and that we were thinking about thermal bridging and things like that. So there's a lot of thought gone into this renovation. And then we added a warm roof. The roof actually wasn't damaged, but we just wanted the extra insulation, so we added that and added solar panels. So that's that PIR that we're talking about. That the membrane's glued to, and then that timber's inserted in there for the fixing for the solar panels. So there's 2 layers of insulation. One is continuous, and then the timber sits on top of 1 layer of insulation. So if you talk nicely to the structural engineers, they'll usually let you have thermal bridge-free construction, whether it's concrete or whether it's a warm roof, whatever it is. Yeah, so the other thing we did with that job is we put external insulation on concrete block, which is another good renovation tip. So if you've got existing concrete block, a lot of the time concrete block walls have been built inside out, so there's a bit of thin layer of insulation. There's what's called strapping and lining, so there's some battens and some plasterboard on the inside, and really that's inside out. We want the insulation on the outside. So if you can do it and fix insulation to the outside and then put a plaster finish over it, that's a really good way of dealing with a really poor performing concrete block wall or even a concrete wall. So yeah, I don't know why I put this image in here, but I just it's good for a laugh. I think that's our last slide. So if there's any questions, we'll go to the questions. No questions. We were too thorough. Hey, thanks everybody for tuning in today. And yeah, the next event for Superhome Movement is our Superhome Summit, end of year soiree. And so if you jump on the website, you can register for that. And we'll be launching the Superhome, sort of a soft launch for our participants of the Superhome design guides and the Super Reno guide. And that's our big project that we've been working on. So first 2 minutes, yeah, we can share the slides, and this is recorded as well, so that'll go up on the website if you missed the first part of this. So that's no problem. And actually all of the previous webinars are on the website too, recordings of those.
Something else to get excited for next year is the 10th anniversary of the Superhome Movement.
Yeah, so crazy, eh? 10 years next year. So and so we'll have another big party early next year, or sort of maybe around Easter.
Yeah.
Yeah, so keep an eye out on the events page of the Superhome website. And a really good way to just keep your ear to the ground is just make sure that you're on the mailing list for the email newsletter. So if you go to the superhome.co.nz, you can sign up for the newsletter. Thanks everybody for joining us, and enjoy the rest of your day.
Is that? Thank you.
See ya.